Welcome back. How was that exercise? Does your brain hurt from all this confusing sequence? Let's actually start off with the recursive function this time. Because in this case, the recursive function is actually a lot simpler to think about. All we would do with our recursive function is to say, well, the base case is going to say number, or n, is going to equal 2. If that's the case, simply return. Actually, if we look at the sequence, we see that if the index is 0, the answer is 0. If the index is 1, the answer is 1. And if the index is 2, then the answer changes to 1. So instead, our base case can maybe just simply be if n is less than 2, we're always going to just return whatever the n is. So if we say 0, it's going to return 0. If we say 1, it's going to return 1. If we have an index higher than that, well, then we have to do some recursion. And all we're going to do here is have another return statement and say this function. I know that this function is really, really long. We can probably make it shorter to just say fib. And I noticed that we don't need the iterative here. That will make it a little shorter. There you go. Now all we're going to say is fib is going to equal n minus 1 plus the same thing, n minus 2. Because remember, the sum is always, the answer is always the numbers 1 and 2 before it. So we're just adding the numbers 1 and 2 before our sequence. And that's it. If we run this function, let's say Fibonacci recursive of 3, and I click run, I get 2 because 0, 1, 2, 3 is 2. Let's do 8, which should give us 21. And I click run, or give 8, I get 21. Nice. And if I do 0, I get 0. If I do 1, I get 1. If I do 2, I should get 1 right here. Nice and simple. Well, I don't know about simple, right? You really have to get comfortable with this before you truly understand what's happening. But I have a little diagram to help you here. All we've done is simply this. If I added 7 here, our recursive function is going to get 1 less than 7 and 2 less than 5. And then within those functions, do the same thing. 1 less than 6, 2 less than 6. 1 less than 5, 2 less than 3. And it's doing all of these, all of these, all of these, until we get to fib of 1, 2, where we have our base case that returns that number. So this becomes 1. This also becomes 1, and then it keeps going, keeps returning until we get to fib of 7. Now, this is a diagram that we're going to get back to, but you see we're doing a lot of calculations here. But simply put, this is all we're doing. Now, I said that the recursive approach is actually simpler than the iterative approach. Let's have a look at what the iterative approach would look like. We'll create an array, and there's many ways of doing this. This is my preferred way. And this array is going to have the initial items of the sequence, 0 and 1. And this is going to, first of all, return the array an item of n. We're creating this array and then grabbing whatever index the user wants. In our case, if the user requests 0 or 1, we already have the array pre-filled with 0 and 1, and it's going to return the same. But we still need to calculate for all the other ones. That's where we do a for loop and say let I equal 2, because we're going to start adding when the index is 0, 1, 2 to start filling this array. We'll say I is less than n plus 1, or we can do equals here if we want. We'll leave it at that for now, and we'll increment I++. And in this loop, we're going to keep going until we hit the number of index that we're interested in, and all we're going to say is array.push array I minus 2 plus array I minus 1. Similar to what we did before, we're just summing the previous 2 numbers and pushing it to the array. All right, now let's see if this works. I'm going to comment out this one and just do the iterative approach. I get 2. For 3, what about index of 8? I get 21. Perfect. And then if I do index of 0, index of 1, and index of 2, should be 1. Perfect. Now, I said that the recursive approach is simpler than the iterative approach. Now, that's my personal opinion. You might not think that. You might think that this was quite easy. But to me, this reads a lot nicer than all this thing that we're doing. And this is something we're going to get into in the next video, where we talk about the trade-offs between the iterative and the recursive approaches to these problems. And why, maybe you're wondering right now, why would we ever write anything recursive if you find this confusing? We'll get to that. But the one thing I want to show you is something that we just learned here that is new to us. What do you think the big O of these two functions are? Well, in our iterative solution, the big O is linear time, right? It's O of n. Basically, we're just iterating through the loop n minus 2 times because we're skipping the first 2 items, which in turn makes it O of n. But what about the recursive approach? Remember the diagram I showed you? That's a lot more calculations than just the 7, right? We have a lot of function calls that happen. In this case, in the recursion solution, it takes what we call exponential time. The size of the tree exponentially grows when n increases. If Fibonacci number was 8, we would have this tree as well as another tree underneath the fib of 8. So what is the big O of that? This is very exciting because we're learning about a new big O notation. We're learning about this one, exponential time, which can be seen with recursive algorithms that solve a problem of size n, 2 to the power of n. If we go to our big O cheat sheet, this is O 2 to the power of n. You see how much it increases? That's pretty bad. It's bigger than even O of n squared, the 2 nested for loops. Exponential time means every additional element in the Fibonacci sequence, we get an increase in function calls, exponentially. And here's a fun little trick. Although this is O of n, the iterative approach, this function, because it's O of 2 to the power of n, if I run this function, let's say if we do 10, I get a result. If I do 15, I still get a result. What if I do 20 here? All right, it's starting to get bigger and bigger. If I do 30, if I do 40, do you see how much longer that took to calculate? Because our time complexity is increasing more and more. If I do 43 now, you'll see that we're waiting and waiting and waiting for the calculation to happen, and eventually the browser comes up with the calculation. As a bonus question, think about how many calculations Fibonacci 43 required. This, although might be more readable, is not an ideal solution. As you can see, big O time complexity is pretty big. And this is something that you might get asked in an interview. And I know what you're thinking. Andre, you just taught us about recursion, and it's not even good. It's slow, it's confusing. Why would I ever want to use recursion? In the next video, I'm going to talk about this trade-off. Why would you ever use recursion over something that is iterative? Why would any sane person do that? And as you'll find out, there are some pros and cons. And as a matter of fact, a function like this, such as Fibonacci sequence in recursion, can be made to O of n using something like dynamic programming and memoization, which we're going to talk about towards the end of this course. And we're going to get back to this. But let's finally answer the question in the next video. Why would you ever use recursion over something iterative? I'll see you in the next one. Bye-bye.